Let's proceed. Now, this week, like I said last week, we're going to assume that, or we take it for granted that you already have had your first statistics class. So we're not going to repeat the processes of how to calculate the mean and standard deviation. This class is going to focus much more on inferential statistics, but entirely on inferential statistics. So the descriptive statistics foundation is taken for granted. So today I'm going to summarize with examples the foundations of inferential statistics. So I'm going to pull up some slides, but the simple thing is this. In statistical analysis, we have, like we said, what we call the descriptive statistics and the inferential statistics. And descriptive statistics essentially summarizes data, puts them in tables and charts. You get a first, I will say, a first view, a basic view of what the population looks like. So you have the population that you're trying to study, because in statistics, you are focused on studying a population. Okay, and that population could be a population of trees, it could be a population of children, it could be a population of cars, houses, you name it. But in statistical analysis, we do not have access to population information. Because you have the population information, of course, you can summarize the characteristics of that population and very easily say, this is what the population is, because you have the exact information. But because we do not have population, we don't have access to population data. So in statistical analysis, we focus on the sample. So we use the sample and we use information from the sample to make judgments about what the population could look like, because the information from the sample, since it's a sample, which is a selection from within the population, we cannot say it's exactly what the population looks like, but in all likelihood, this is what the population would look like. Okay, so, and what is the foundation of that? The foundation of inferential statistics is based on, again, what we studied in statistics 1. The foundation is based on what we call a distribution theory, a theory about how data is distributed within a population. So our foundation would then be the standard normal distribution, which we also use for deriving the T distribution. The T distribution is what we use for small samples, and we use the standard normal distribution for large samples. So let's go and see what we have. All right. You can see my screen?
Yep.
All right. So let's move on. So what we call inferential statistics, our subject is always the population. And we want to study the characteristics of the population. For example, average income, average travel time, okay, average GPA, average weight of fish in a fish pond. And we use information from a sample, which is a selection of a size n, to make a judgment or inference about the population. That's essentially what inferential statistics does. Like I said, we do not always, in fact, we do not usually have access to the population information. We always have access to some sample. Okay, and so for today, in this module, you will learn how to describe the standard number distribution, which is the foundation, and how we use it to calculate probabilities. We will then introduce inferential statistics by calculating what we call point estimate of a population, and then we calculate or develop confidence intervals, which gives us a range of values of what the population could look like, and interpret the confidence interval for population means and population proportions. Now, like we said, we're going to use the standard normal distribution. What is the standard normal distribution? When you get information, when you get to a population, for example, or when you get a sample, what of course happens is that if you look at any variable, any random variable, okay, let us say you look at a population of children, you look at the population of houses. The prices of the houses are not going to be the same. So there's going to be different prices, and so essentially what we look at the data, we said the prices are distributed. Okay, there are low prices, there are high prices, there are prices in the middle, and so when we look at the data, then what we do is we look at the distribution of the data. Okay, how is the data dispersed? Okay, there are small values, and those small values, there may be very few of the houses that have the small values. There are very few of the houses that have very high values, and a lot of the values of the houses are somewhere in the middle. Nevertheless, the values of the variable can be described by what is called a normal distribution table. Okay, the normal distribution table is bell-shaped, it is symmetrical. It has a value, an average value, and the average value of a normal distribution is 0. So it's based on some imaginary random variable called Z. Okay. Right. It's based on an imaginary variable called Z, and the average value of Z, the mean of Z, mu, as you can see here, the average value of Z, which is called mu, has a value of 0 and has a standard deviation of 1. Now, every distribution, whether it is a normal distribution or any other distribution, is described by an area. Like in the case of the normal distribution, it is symmetrical, and the area of under the curve is always 1. Okay, the area under the curve is always 1. So if you measure the area under this curve, it's always 1. The mean value is 0, and the values of Z are distributed along the bottom here and go from -infinity to +infinity with a mean of 0. Okay. Now you use this to ask yourself, what is the probability that Z will have a value within any range? Okay, that tells you the percentage of the values of a variable that are within any particular range. For example, what is the probability that a random variable will have values between 6 and 8? between 15 and 25. And here we are looking at miles, for example. What is the probability, what percentage of students travel between 15 and 25 miles to school? What percentage of vehicles, of tires of vehicles last between 7,000 miles and 15,000 miles? These are the kinds of things that you use the random probability distribution to calculate. And in order to do that, we standardize the values and call them Z values, okay? And so we calculate a Z, and a Z value is X minus mu divided by the standard deviation. Let us see. Okay, so like we said, the standard normal distribution is based on a hypothetical, an imaginary random variable called Z. Z has a value of 0 and a standard deviation of 1. Okay. All right. So let us here use some practical examples to illustrate how Z is used. Okay. We said these are examples of imaginary probability of Z random variable with a mean of 0 and a standard deviation of 1. So what is the probability that Z has a value between 0 and 1.3? Okay. You see there's a table here. Okay. And that table, we have a bigger one. But what is the probability that Z has a value between 0 and 1.3? Okay. So the middle here is 0, and to the right of 0 is 1.3. So what is the probability that Z has a value between 0 and 1.3? And so you calculate the area under the curve here, as you see the shaded area under the curve. So, for example, what is the probability that Z has a value between 0 and 1? That is 0 and 1. It is 0.3413. Now, let me just stop share this and pull up the table, the full table. Okay, can you see my screen?
Yes.
Okay. All right, so what is the probability that Z has a value between 0 and 1? Here is Z, here is the value 1. The probability that Z has a value between 0 and 1, see 0 here, and you go to 1. It's 0.3413. You can see it? Okay. Now, remember that Z is symmetrical. Okay, that is, Z is cut in half by its mean 0. And so half of Z is on the right and half of Z is on the left. The total area of Z is 1. Therefore, this half of Z to the right has an area of 0.5. And the other half of Z also has an area of 0.5. If you go one step to the right of 0, it's equal to going one step to the left of 0. Therefore, the probability that Z has a value between 0 and -1 is the same thing as the probability that Z has a value between 0 and 1. So you can use this table to calculate the probability that Z has a value between 0 and +1, and also the probability that Z has a value between 0 and -1. Okay? So this is the table that you use for making those calculations. I will stop share this and go back to our PowerPoint. All right. So this is what I was asking earlier. What is the probability that Z has a value between 0 and 1 and between 0 and -1? You can see that the two areas are the same because one step to the right is equal to one step to the left. What is the probability that Z has a value between -1 and 1? So you are crossing from the left to the right, and so the probability is the sum of these two. You following me?
Yep.
Okay. And so you can use
So it's double the amount, right? From negative
because
to 1.
because you're going from the left to the right, and you're going from the left and you are crossing 0 and going to the right. Okay. Okay. What is the probability that Z is greater than 1.6? So now you are looking at only one side of the distribution. And so since the area of 1/2 of the distribution is 0.5, and you are looking at a tail, so you take 0.5 minus 0.4452, 1.6 is 0.4452. And since you have already taken off 1.6 and you are going strictly to the right, then the area is 0.5 minus 0.4452, which is 0.0548. Okay? This is how you're going to solve problems using the normal distribution. All right. I'm going to come up with unpractical problems. Okay. Let's take an example. Suppose you have a company that makes tires, and the average life of the tires is 67,000 miles, and the standard deviation is 2,050. Now, the probability that a tire will last between 64,000 and 72,000 miles. And so here you have X between 64,000 and 72,000. So you calculate Z equals to X minus mu over sigma. So you transform the values to Z values. You transform these X values to Z values. So the first Z is 72,000 minus 69.7 over 2050, which is your Z becomes 1.12. And the area under the curve is 0.3686. And then you calculate the second Z, 64,000 minus 69,700, which is minus 2.78. So you are on the left side of the curve, and the probability is 86.59%. All right. So what is the probability that a tire will last between 64 and 72,000 miles? Okay. And so you add these two probabilities and you get 86.59% because one side is 36% and the other side is 49%. Okay. You can now use this principle to calculate what we call confidence intervals. Now, what is a confidence interval? Okay, what is our objective? Okay. Now, the problem when we are doing statistical analysis is we look at a population, and for example, you ask, what is the average travel time? You don't know what it is, but you want to use information from a sample to estimate what the true average is. Okay, that is what we are trying to do. Point estimate, we call it by X. We take a sample and calculate a sample estimate. We want to use information, this sample estimate, to make an estimate of the true average. This is the sample mean, and you want to use this sample mean to make a judgment about the true mean. We want to use information from a sample proportion to make a population about the true proportion. Okay? And so we use the formula x bar plus or minus z times sigma over the square root of n. And here's an example here that you can walk through. So for example, a sample of managers make an income of 45,000 with a sample standard deviation of 3,500. So we construct a 98% confidence interval for the income of managers in this industry because we don't know what the average income of managers is, and we are trying to estimate what the true average is. Okay, so we use the sample mean. We get a z because we have a 98% confidence interval, and we come to the conclusion that the average salary of managers is between 44 and 46,000. All right. Okay. So now, on the basis of this summary lecture, which I'm going to post, do you have any questions about the homework assignment?
No. All good, Professor.
Okay. All right.
Yes.
So I'll post this in case you want to look at it again, and I'll see you all next week. Okay.
Yes, yes. I think you submitted the PowerPoint too, so the
Yes.
information is there too.
All right. Okay. This particular PowerPoint that I use now, I didn't submit it, so I'm going to post it.
Okay.
All right.
All right.
Okay then. Good night.
All right. Good night.